Hello. We have been discussing tunneling of electrons through a potential barrier. So today we are going to discuss the electrons tunneling through a periodic potential. In the context of periodic potential, we have already discussed chronic penny model, but in that model we have considered a delta function kind of potential barrier which is not quite realistic. If you have an array of atoms even in one dimension, if you consider a one dimensional solid, you will have potentials that are not really like delta functions in the barrier. Rather, the potential would go to the potentials will have a sharp dip wherever there are atoms, and everywhere else it will behave like a barrier. So in that context, we better choose an arbitrary barrier to understand exactly what happens realistically, and then we will understand whether chronic penny model is realistic or it gives us some understanding far away from the real physics of a solid. Let's discuss that. So we can consider a set of periodic potentials like this, say, that extends to infinity on both sides. If we consider this to be 0 in the x-axis, this is the x-axis, and this is the potential axis, Vx. If we consider this to be 0, this point is A, x equals A, here x equals twice A is the lattice constant, and so on. Now, if we consider one such profile of the potential, say this one here, then just like earlier, we can say that this is the potential axis Vx, this is the x-axis 0 A, this barrier height, let's say this is V0, the incident electron wave, it has an amplitude AL from the left hand side, the one that moves towards the right in the right hand side is AR, and BL moves this way in the left hand side, BR moves this way in the right hand side of the potential profile. So if we consider a one dimensional potential that is periodic in X, and V0 is the potential within a unit cell. So if we have the potential, if we consider a unit cell, the unit cell is given by 0 less than equals X less than equals A. This is the unit cell. Now, we can consider the electron tunneling through the potential that is drawn here, and it so we are considering a region. We have a lead at x less than equals 0 and another lead at x greater than equals A. and in between we have the potential that we have drawn here. So, if we have this kind of a situation, then the wave function in the left hand side of the potential, that is the left hand lead, would be given as psi Lx equals Al e power I qx plus Bl e power minus I qx. This is for x less than equals 0. So, we have discussed this kind of wave function earlier also. Now, we are doing it in terms of the transfer matrix elements. Psi r x in terms of transfer matrix elements can be written as S11 Al plus S12 Bl e power I qx plus S21 Al plus S22 Bl e power minus I qx, where we have this q, which is a function of the energy of the electron, is given as twice m e over h cross squared, square root of this quantity. This is the propagation wave number in the leads. So, here we look for a solution that satisfy the boundary conditions at x equals 0 and x equals a. So, what are the boundary conditions that we have? We have Bloch theorem now in mind. So, at those points, what does the Bloch theorem require? The Bloch theorem required that psi r at x equals a has to be equal to e power I k a psi l at x equals 0. This is the requirement of the Bloch theorem. And if we consider the boundary condition for the first order derivative of the wave function, we can write d psi r dx at x equals a. This quantity has to be equal to e power I k a times d psi l dx at x equals 0. Note something interesting. Here the value of x is a, here the value of x is 0. We are equating them and calling them to be, so calling this condition to be a boundary condition because of the periodic boundary condition. So, we have periodic boundary condition at hand. That means this point and this point are equivalent to this point, equivalent to this point, equivalent to this point, and so on. And that notion of equivalence has this kind of a factor e power I k a, that is something we obtained from the Bloch theorem. Now, if we have these two boundary conditions satisfied, then we can obtain the linear homogeneous equations for the arbitrary coefficients a l and b l in these equations. That can be written as S11 e power I q a, S12 e power I q a, S21 e power minus I q a, S22 e power minus I q a times a l b l. This quantity equals, according to these boundary conditions, e power I k a l b l. This equation shows that the 2 by 2 matrix has an eigenvalue e power I k a. This must be an eigenvalue of this matrix. If that is true, and if this matrix is unimodular, that means the determinant of this matrix is 1, that means the product of the eigenvalues is 1, then the other eigenvalue must be e power minus I k a. Then the product of these two eigenvalues would be 1, which is the determinant of the matrix. Okay. If we have that, what is the trace of this matrix? The trace of the matrix is the sum over the eigenvalues. If we sum over these two eigenvalues, e power I k a and e power minus I k a, we will obtain twice of cosine k a, because the trace is the sum of the eigenvalues. Now, if we look at this matrix, the trace is S11 e power I q a plus S22 e power minus I q a. So, the matrix, the trace and the determinant, they remain invariant under a unitary similarity transformation, and the unitary similarity transformation will give us the diagonal elements e power I k and e power minus I k, the off diagonal elements 0. So, we can still write that the trace is this twice cos k a, and we will have to satisfy a compatibility equation for everything to be consistent. S11 e power I q a plus S22 e power minus I q a, that is the trace of this matrix. This has to be equal to the trace of the matrix that we have obtained from the other method, twice of cosine k a. This is the compatibility equation that must be satisfied. So, this equation is similar to what we have obtained in the context of chronic penny model. Now, it is convenient to express that equation in terms of transmission amplitude. The transmission amplitude is given as T equals the absolute value of T, that is the modulus, times the phase factor e power I phi. So, this is the expression of T in its polar form. If we do that, we can write S11, which is a function of energy, as 1 over T star, that is also a function of energy, equals 1 over T e power I phi, which is also a function of energy. Now the compatibility equation by this kind of a transformation becomes one over the absolute value of TE cosine phi E plus Q times A, this equals cosine of Ka. Phi E and T, the modulus of TE, these are the phase and the modulus of the transmission amplitude. The compatibility equation can be satisfied only for the values of energy for which the magnitude of the left hand side, that is this part, is less than equal to 1, because cosine of k cannot be more than 1. So, if we have this quantity, the absolute value of this quantity less than equal to 1, then this compatibility equation would be satisfied, otherwise it won't be compatible. So, it is important to analyze the band structure produced by the periodic array of barriers from the point of view of electron tunneling. The transfer matrix that we have obtained earlier for a single barrier, if we consider that in the present case, the energy band would be given by the real part of cosine hyperbolic beta b plus I times q square minus beta square over twice q beta sine hyperbolic beta b. Times e power I q a minus b, real part of this quantity, that has to be equal to cosine of Ka. Now, if we compare with the chronic penny model, we can write that A minus B equals the width W, and if we put that in the above equation, we get cosine hyperbolic beta B cosine of QW minus q square minus beta squared over twice q beta sine hyperbolic beta b sine QW. This quantity equals cosine of Ka. So, with this equation we see that even for an arbitrary shape of the potential barrier, in case of periodic potential, we did not consider any chronic penny like delta function barrier here. We have considered this smooth shape of the barrier, and that is arbitrary. We did not really use the shape of the barrier anywhere in the mathematics that we have considered so far. we have seen that we can still obtain a condition like the chronic penny model. So, the gap, energy gap, the prohibited energy region that we have seen in the energy spectrum of electrons subject to a periodic potential, weak periodic potential, is obtained for any arbitrary shape of the potential barrier. It is not really dependent on the shape, exact shape of the potential barrier. So, this is a great lesson that we have learnt from this exercise.